So just a couple of the logistic things. So obviously homework is due later this afternoon. Again, that's going to be downstairs in a 240 Corey, so hopefully you guys are well on your way out with that. Other reminder is that next week there'll be no lectures because we'll be, I'm assuming, pretty much everybody at ISC. So we'll resume the following week. But just as a reminder, there will be a new homework going out. It'll be due probably 2 weeks from today, depending upon sort of how far we get along with the lecture material for today, to make sure you guys have enough time to sort of get all the stuff you need for that homework. We may push it by a couple days or something like that. But again, just be on the lookout for the next homework. It will be going out fairly soon. So before we sort of dive into material we were talking about last time, any questions either on homework or material or anything like that? Okay, so no questions. Let's go ahead and sort of go back into what we were talking about last time. So I believe where we ended last time was starting to talk about essentially the output impedance of these cascoded structures. And in particular, I sort of asked the question as to what was kind of the best way to choose the bias point of the center node, let's just call that Vx right there, inside of a cascode structure. And we said that we could always set that to be equal to some k times the V star of the bottom device. So let me call M1 the bottom device. So that would be like the V star of M1. Okay? And what we basically said was that below some certain drain to source voltage across that net cascode structure, basically it didn't really matter what choice of bias we used, right? We were basically going to get roughly the same output impedance overall. But as long as we got sort of a higher drain voltage, then actually you would start seeing really a big difference between the cascoded versions and the non-cascoded version. And more importantly, we said that basically if we had sufficiently high drain voltage, we would indeed start seeing a difference between things where we applied a larger drain bias across that bottom device versus a smaller drain bias. And kind of the take-home message was really that exactly how we bias it probably is not super critical, but in general, if you want to do it, you probably want to bias it reasonably high, just to make sure that indeed if you get the high drain to source voltage, you will actually get also the high output impedance. Okay? And the whole point there was just that, if you had lower drain voltage, there really wasn't much of a penalty for having made that choice in the first place. Okay? So that's really just sort of a reminder of, I think, the last thing that we talked about last time. It turns out that anytime you sort of do these cascodes, you need some kind of bias voltage for the cascode itself, exactly to control that internal node voltage that we just talked about, that Vx. Okay? So there's a whole bunch of circuits you can come up with to do that. But I'm actually not going to spend basically any more time on it other than maybe to just mention a couple of important things. Basically because as we just said a second ago, largely speaking, it's not super critical to get that exactly right, as long as you're sort of close enough that you will actually sort of get the higher output impedance at the range of VDS you're really interested in. Okay? So also, I'm not going to spend a lot of time on this because I'm going to assume that you've seen this before in something like EE140 or an equivalent class you've taken. If not, there's plenty of sort of material on this in Gray and Meyer, so definitely feel free to go and sort of take a look at that. Again, just sort of look for high swing cascode biasing. You'll see there's all kinds of sort of tricks and tips that they'll give you there. But just user beware, a lot of the sort of design equations there are based upon long channel devices. So obviously when you get to the short channel devices, they may or may not exactly hold as sort of advertised in the original textbooks. But nonetheless, the good news is as long as you do something reasonable, quote unquote, it's probably not going to matter too much as long as you're sort of getting that drain voltage high enough that you will indeed get the output impedance you're interested in. Okay? So just one thing that I will sort of briefly mention, this is just an example of one of these sort of high swing cascode biases. Particularly the way that it was done here was essentially they took this sort of diode connected device, and if you pay close attention, you'll see that it's actually smaller than the devices in the cascode or in the current source itself. And this was done intentionally to generate a higher gate voltage here versus what's done in the other legs. Okay? Now, that's actually not, I think, too particularly interesting. What I did want to ask, however, is there's kind of an interesting, I shouldn't say trick, but a kind of interesting and perhaps somewhat important point as to how exactly I set up this circuit here to actually even do the current mirroring function. So in particular, I want to contrast what's drawn here against what I might have been able to do or what I might have tried to do in a sort of naive way, which would have been something like the following. Right? If I wanted to do the current mirror, I could have just done something like, at least structurally, that would look like this. Okay, so let's just call this VB here. So I could have indeed just connected that VB to the Cascode device over there, and then said, okay, this is sort of the point at which I'm taking my output current. So maybe I won't draw a current source here. I'll just say that's my sort of output current right there. Okay. So the question I want to ask you guys is, why do I claim that actually what I did in the real slide here, in other words, what's drawn in that cadence schematic, why is that probably a much better way of doing things in terms of just the current mirror itself versus what I drew on the right? Yeah?
Well, on the right you kind of have an arbitrary bias voltage, while on the left it's like exactly right.
Okay, so you said I have sort of an arbitrary bias voltage on the right-hand side, versus on the left it's sort of exact. Now, so which bias voltage you're referring to? I basically agree. I just want to make sure we're very clear as to what the difference is. VB. Oh, okay. Well, so I'm still going to use actually the exact same VB in this circuit as I am going to use in this circuit. Okay, so I'll claim that that maybe is not different, but there is an important effect due to not necessarily that VB per se, but due to the structure of this circuit. I'll maybe give you guys a reminder. What did I say was the absolute #1 rule about matching in analog circuits? What was that? VGS. Okay, no, the VGS is important, but I'm saying even more simply than that. When we talked about doing analog layout, and I said, if you want things to match, what do you have to do? Yeah, you have to make everything exactly the same. Okay? Now notice, if I'm doing a current mirror, indeed, I'm trying to get two things to match to each other. Right? I'm trying to get, for example, the current in this branch right there to be some multiple of the current in that branch. Okay? So why is it that I claim that what I did in this left-hand picture is really much, much better than what I did in the right-hand picture?
I think it's because the drain voltage on M1 is shielded, so it's more likely to actually match the drain voltage on M3.
Yeah, exactly. Okay, so the big trick here is that let's just call this M1 and let's call this, M3 over here, and I guess we can call that M2, right? So in that picture on the right, notice this structure over here is a cascoded current source, right? The structure on the left that should be a copy of it is not cascoded, right? So the more, let's say, technical explanation was that indeed, if you went to this kind of structure here, now this drain voltage is much more likely, in fact, almost guaranteed to be the same as this drain voltage, right? Because now the cascode is actually forcing those two drain voltages to be the same. Whereas in this case, that drain voltage is whatever the gate to source voltage is, which by no means is going to be the same as what this point here is. Okay? So again, really the most important meta point is that anytime you want two things to match, you absolutely have to make sure they are exactly the same. And exactly really means exactly. If one of them has a cascode, the other one has to have a cascode. If one of them, has some weird, wire going off to oblivion, because you decided to add it there for whatever reason, the other one had better have the exact same thing too. Okay? Now, obviously, depending upon what it is, it'll be more or less effect as to whether or not it'll cause a huge matching error. But nonetheless, if you want to do things right, you had better do things exactly the same. Again, in particular for these sort of cascoded current sources, very classic mistake is to not make the current mirror itself also cascoded. Okay? Because again, if you don't make it cascoded, structures are not the same, A, even from just a layout standpoint, but B, more importantly, you're not really sort of controlling the drain voltage bias to be the same on the two sides. And therefore, indeed, you will get potentially very large errors in that current mirroring ratio. Does this make sense to everybody? Or? Okay. So we talked a little bit about sort of cascoding, but turns out in modern technologies, even if you do a cascode, there's still a pretty sort of unfortunately low limit in terms of the gain you can get. Because, for example, if I tell you that the GMRO I can get from a device is something like, let's say, 10, then even with a cascode, I could maybe only get sort of a gain of about 100, right? And oftentimes, I'm going to want open loop gains of something like 1,000 or even 10,000 or somewhere in that ballpark, okay? So turns out there's going to be one sort of fairly, well, at least conceptually simple trick we can play to make that happen. and hopefully do it in a way that actually doesn't basically run into headroom constraints. Okay? So in particular, we said that if I just had my normal cascode, or single cascode I should say, right, that would look something like this, right? And as we've said several times now before, the output impedance of that would be something like GMRO times RO. Okay? So if I want to get even higher output impedance, at least the old classic textbooks would say, well, okay, fine, just cascode it again. Right? Just go and add yet another cascode device. Right? And then you'd get something like GMRO squared times RO. Now, hopefully the obvious thing that's kind of bad about this particular configuration is that now you need even more voltage drop across the thing to actually make sure you really do get that high output impedance. Okay? But so here's where we can actually sort of remind ourselves as to how the cascode was working in the first place, and actually come up with a way that will allow us to improve the output impedance, actually without sacrificing the VDS or the Vmin whatsoever. Okay? So just as a reminder, how was it that the original cascode was helping us in terms of output impedance in the first place? What was it doing? What was the sort of mechanism that we discussed last time? Yeah, exactly. It was basically taking that Vx and making the change in voltage on Vx much smaller than the change in voltage across the whole cascode, right, or across the whole current source. Okay, well, if my single cascode device is not good enough to basically keep that Vx fixed, what can I do to make it even more fixed than it was before? Yeah, okay, you said an op amp. Well, what are you going to do with the op amp? Yeah, exactly. I can basically take some sort of amplifier, right, and then put it into feedback to drive the gate of that cascode to try and make sure, and of course I'll need some magic reference voltage here, to try and make sure that really that node is absolutely pinned, or at least much more pinned than it was before. Okay? So by the way, this is just another example of, in general in analog, when you have a problem, throw feedback at it. Obviously, there's different ways of doing it, but this particular example is indeed a very good one. Okay? So now, just to be totally clear, let's say that that amplifier had a gain of AV. Okay? What would be the new output impedance of this whole structure now? By the way, if you guys remember when we looked at the original cascode, we said there was a Vx there, and we sort of compared that to the swing on the VDS. What did we say was the relationship between the swing on Vx and actually the swing at VDS? How are those two related to each other? Yeah, it was reduced by the GMRO of the upper transistor. Okay, so now if I have some small movement on Vx, what's going to happen on the gate of that transistor there? It's going to get amplified by the gain of the amplifier, right? That's kind of like saying that the GM of the transistor was increased by the gain of the amplifier, right? Because now instead of seeing, for example, in this configuration, if I just had a bias voltage there, now the VGS would have changed by just Vx, right? Here, if I have some change in Vx, what's the change in VGS? And by the way, I want the precise answer this time. What is it? I heard somebody whisper. Just speak up. Is it AV minus 1? You're very close. We just need to flip one sign somewhere. There we go. It's 1 plus AV, right? Because notice, even if that gate didn't move at all, you would have gotten a change of Vx, right? So it's actually 1 plus AV is the change in gate to source voltage. So because of that, you can actually basically say the equivalent GM is also 1 plus AV, larger than it was before. Okay? So if you think about it, that all put together basically means that the output impedance of that structure is 1 plus AV times GMRO. I'm sorry, times GMRO times the original RO. Okay? Does this make sense to everybody? Or? Now, by the way, I want to point out this. I was kind of careful or pedantic about that 1 plus. Usually, if the AV was big enough, I would have just dropped it. But keep in mind that 1 plus, because we're going to do something in 1 second to kind of analyze this structure a little bit more carefully. That if you forget about the 1 plus, will perhaps confuse you a little bit. Okay, so just keep that in the back of your head for a second. All right, so this sounds great. And indeed, this is a very useful technique to get much, much higher output impedances. But there's one thing that should be sort of like immediately, an alarm or a bell or something was going off in the back of your head as soon as I did this. So anytime you sort of have some feedback circuit, what's like the first thing you're supposed to worry about?
Stability.
Yeah, stability, exactly. Okay? So if I'm worried about the stability of that feedback loop, because indeed I've now got a feedback loop in my circuit, what's let's say the first thing I need to think about, or how will I sort of analyze whether or not this thing is indeed going to be stable? And I'm just going to redraw the circuit, by the way, while you guys answer that question. So what is it I need to worry about? How am I going to figure out whether or not this whole thing is indeed going to be stable or not? Yeah, I basically have to analyze what the poles are, and perhaps what the zeros are as well. Okay? So in particular, I'm going to, just to make life a little bit easier, I'm going to do sort of an open loop analysis, meaning I'm going to just try and find what the poles and zeros are if I break the feedback loop. And in particular, I'm going to break it at this point here. So I'm going to drive a source in from here. I'm going to measure sort of the return voltage there. Okay? All right, so first of all, and let me actually just, maybe add things in a little bit to make it more clear, or make it obvious sort of what I'm looking for. So let's ignore all of the capacitors in the circuit, except for the two that I'm drawing here. Okay? So I'm going to assume there's some capacitance at the output of that amplifier there, and there's some total amount of capacitance at this source node here. Okay? So hopefully it should be pretty obvious that if I've done that, and at least if my RO of the transistor is infinite, I can only have 2 poles here, right? One pole, of course, is going to be from the amplifier, right? That's my sort of first pole. And my other pole is going to be just at that source node due to the capacitor that I added there. Okay? And let's even label that capacitor. Let's just call it, I don't know, let's call that CX. Okay? So let's do perhaps the easier one first. Where is the pole due to that CX going to be? What frequency is that going to be at? Yeah, okay. So basically, let's call this M2. Let's call that M1. Right? At least if that transistor effectively has no output resistance, it should just be at GM2 over CX. Okay, and by the way, I'm ignoring minus signs, but you should keep in mind the poles indeed should be in the left half plane. Okay? So indeed, that should be at GM2 over CX. Now, by the way, what should that frequency be? Is that like a high frequency, a low frequency? Like, where should that be? It should be high. Why should it be high? GM's large, you mean? Okay, well, let's be a little bit careful. So you're right, it should indeed be high, but it's not just because GM is large. Like, what does this GM over CX kind of remind you of? Or rather, what is that CX probably even coming from in the first place? Yeah, okay, you said it should be near the FT, right? And indeed, that's right, because at least if you do things properly, then the CX should largely just be dominated by the transistor's parasitics itself, right? It's never really going to be exactly FT, because there's always, I've got 2 junctions here, I've got another gate over there. But the zero order, indeed, it should be pretty close to the FT of the device. Yes?
Did you say why we're ignoring the RO?
We are ignoring the RO for now. I'm ignoring the RO largely to just make the point, because it'll make things more complicated if you include the RO. But as long as the GMRO is high enough, that's a very reasonable thing to do. That wouldn't really change, in particular, it wouldn't change the location of this pole very much. It's just that there'd be extra poles that we'd have to think about. We'll deal with that in 1 second. Okay? So, Indeed, this should basically be at the FT of the device. So, or at least close to it, I should say. Well, if that's the case, then where do you think you're going to want to put the dominant pole? In other words, are you going to want to make number 2 the dominant pole, or number 1 the dominant pole? Because remember, we've got a feedback loop, so we have to place the dominant pole somewhere. Who thinks they want to put it at number 2? Number 1? Okay, well, there's a bunch of people who have no vote. I'm going to fail you guys or something like that because you only had 2 choices, so you might as well have guessed one of them. So, for the guys who said number 1, why number 1? Yeah? Yeah, exactly. So the whole point is, remember, when you're trying to make one pole dominant versus the other, it means you have to put it at a much lower frequency versus the other to ensure that you get sufficient phase margin. Now, okay, maybe before we do that, just to be totally clear, where is that pole going to be at? And let's just assume, by the way, that the amplifier that I drew there has some output impedance, RO. Where is that pole going to be? Open loop. This should be like, 105 kind of stuff. So there's just some RO for that amplifier, and there's some, let's call this, CG. So where is it? There we go, 1 over R out CG. Okay? And by the way, just, let's also say still that thing has an open loop gain of AV. So how far down do I need to place omega P1 relative to omega P2 to make sure that this thing will have sufficient phase margin, at least the 0 order? I'll maybe give you guys a hint. If I had very low gain in that amplifier, how far, would that mean that those poles have to be very far apart? Or could they be reasonably close together? Yeah, they'd be closer together. So more precisely, in general, how far apart do they have to be? Yeah, exactly. So if you look at the ratio of those poles to 0 order, then you should basically place them far enough apart that they're spanning the gain of the amplifier in the first place. Okay? Now, I didn't give you any exact mathematical condition as to what exactly the phase margin of that is, but it turns out that's actually very easy to work out. And I won't do it for you. I'll actually give that to you in a homework. Okay? But indeed, to 0 order, you always have to space them roughly the gain apart from each other. Okay? Because if you think about it, if they're less than the gain, that means you're going to cross over while you have a very substantial effect from that first pole coming into the, or rather from the second pole coming in and changing your phase margin. Okay? So just to make sure that this is really sort of clear as to what all of this means in terms of you actually building that gain-boosted cascode, what I'm going to do is something that will take a little bit of time for us to build up, but hopefully will make it very clear as to exactly how all of this system works, and in particular, what all of the different dynamics you're going to have to worry about look like. Okay? So I'm again just going to redraw the gain-boosted cascode over here on the right. And what we'll do in 1 second is actually draw the sort of frequency-dependent output impedance of that structure. Okay? So again, let's assume we have something that looks like this. So there's some VREF over here. There's some feedback. There'll be, again, some capacitance at that gate there. And we'll put some capacitance at that source node as well. Okay? So now I'm going to draw this rather large. I recommend you do the same because there's going to be a bunch of things going on here in a second. So if I do a plot in the log domain of basically the magnitude of the output impedance versus frequency, okay, and where, again, to be clear, I'm basically looking at Z out over here. So first, and again, I'm going to build this up sort of step by step. Okay? So first, if I really just had the bare transistor with no cascoding whatsoever. Okay, so I really just looked at basically the output impedance of that. That would just be RO, right? Nothing magic there. So that would be essentially just RO over all frequencies. Okay? Now then, if I went and I took that CX and I put it in parallel, right, then what should happen is that at some frequency, my impedance would start rolling off, right, just because of the CX. Okay, so now when I go and I just add the cascode in, at least at DC, what did we say was going to be, what would happen to the impedance? And let me do that in a different color. So I'm just adding in the cascode. What is now the new impedance? Again, at least at DC. Yeah, exactly. And it's just going to be GM RO times RO. Okay? Now, indeed, it will be flat out here for some period of time. What's eventually going to happen? What's eventually going to happen to that impedance there? Yeah, there is indeed still a CX. So what will that cause to happen? Yeah, I see sort of hand motions in the right direction. By the way, it's actually slightly tricky, but we can figure this out. So at least one person sort of did something like this. So maybe just say it in words so I can repeat it for the camera. Yeah, it'll roll off. Okay, so indeed it'll start to roll off because of that CX, right? And in particular, let me just draw this a little bit carefully. It'll do something, roughly speaking, like this, right? Because basically when that CX kicks in, it's just going to short out that source node, right? And so if I'm now looking, for example, out here, right, then indeed what should happen is that when that CX sort of shorts out, I lose the RO on the bottom. Okay? Turns out in the limit, it would probably flatten out to something else over there because you'd get just the RO of the cascode, but don't worry too much about that. Okay? So that's indeed what's going to happen when I add the cascode in. Now let's actually go and add in the gain boosting amplifier. And I'm going to do that in a different color just so it's clear. Oh, yeah, question.
So with the GMRO, or the one that you just drew blue,
Yep.
Why is the pole in a different place?
Oh, you tell me.
I don't know. I mean, it seems like you're just applying a gain to the impedance you see at the source.
Well, okay, so we have to be a little bit careful. So if I did just the regular cascode, then is the impedance at that source node sort of the same as it used to be, or did it actually change? So it actually changes, right? Because I put the GM. Exactly. There's going to be a 1 over GM there rather than an RO. Now, it's a slightly complicated thing to work out exactly where it's sitting, but it turns out that's not going to be super critical in terms of the discussion we're having now. If you're like, we can go on the board and I'll show it to you a little bit later on. But what I'm actually much more interested in is what happens now when I add this gain boost in. Okay? So at least at DC, what did we say happens with a gain boost? Obviously, it should be higher, but, let me do that in a different color. Should indeed be higher, but what is the value, again, at least at DC? There we go. It's 1 plus AV times GMRO times RO. Right? So it got boosted by this 1 plus AV. Okay? Now, is it going to stay up there forever, or is something going to happen? Do we just get 1 plus AV, GMRO, RO, out to infinite frequency, or something unfortunate going to happen? It's going to start to roll off. Okay, there. Great. So remember, the whole reason we got this boost was because the amplifier gave us gain, right? Well, when you hit the pole of that amplifier, that means the amplifier is giving you less gain than you had before. That means your impedance is actually going to start to roll off. Okay? And so particular, it'll start to roll off. Now, and maybe I'll just label it here. This is basically that omega P1 that we had mentioned before. Okay? Now, when it hits that blue line down there, what's going to happen? In other words, when the green curve hits the blue line, Will the green curve keep going down, or will it do something else, actually? What do you guys think?
Should track the blue line.
Okay, you said it should track the blue line. Why?
Because AV is effectively really small.
Yeah, exactly. If you make AV 0, unless somehow I magically made it negative, which, okay, there may be some weird way I could do that. But basically, even if AV goes to 0, I'm still going to get the GMRO of the cascode, right? And remember, at the end of the day, that's what that blue line was, okay? So indeed, once you hit that point, it's basically going to track whatever the blue line was doing, okay? Does this make sense to everybody, or? Now, by the way, just because it'll be useful to us a little bit later, what is the point at which those two meet? What frequency is that? Yeah, okay, there's no 1 plus there. It turns out to be AV times omega p1, but yes. Actually, yeah, I'm pretty sure that's correct. Okay, so that's just AV times omega p1. Okay? Because basically the ratio between those, you might be right. There might be a 1 plus there, but don't worry too much about that particular one there. That's basically at the gain bandwidth of that amplifier. Okay? Does this make sense to everybody? Because again, that's really the point at which the gain basically dropped off sufficiently that now you're just doing whatever the open loop of the cascode was. Okay? So now I'm going to do sort of an interesting thought experiment. I'm going to make this, a little bit more complicated. By now I'm going to actually add in a load cap out at the output over here. Okay? And so now what I'm going to basically tell you is, turns out that that load cap, if I was to draw its sort of impedance versus frequency, would do something like that. So that's just the impedance of the capacitor, which of course is a reminder, the magnitude of that would just be 1 over omega c. Okay? And in particular, this is CL here. Okay, so now just one last color so that everything will hopefully still be clear. Let's try, orange over here. So now if I looked at the output impedance of that entire structure, so in other words, I put that CL in parallel with my gain-boosted cascoded current source, what is that entire impedance going to look like? And by the way, you can start from the simplest point. Okay, you said it's going to follow the lower of the two, and indeed that's exactly what's going to happen, but it turns out there's a slightly interesting effect we need to pay attention to. Okay? So certainly at DC, the lower of the two is going to be just 1 plus AV times GMRO times RO. Right? That's pretty easy. Okay, now I'm going to draw something that's slightly exaggerated, but will hopefully make the point that I'm going to want to make clear. Okay? Turns out it's going to start then tracking down. But if you'll look very carefully, I made that ever so slightly below the black curve. And turns out, once I get to this point, you're going to see a small little kink, and then it'll really track the black curve. Okay? Now there's kind of a couple of interesting things happening here. The first is, as I mentioned, I intentionally made this orange curve ever so slightly below the black curve. Okay? The reason for that just intuitively is if you think about it, if you take two impedances in parallel, right, you're always going to get the lower of the two. Now, we have to be a little bit careful when you have imaginary things in there because you can get resonances and stuff like that. But if indeed we make everything stable, meaning we don't have any peaking or anything, you take two impedances, you're going to get whichever, the net impedance will be lower than either one of them individually. Okay? So indeed, that's why I would argue that this line here indeed is ever so slightly below it. Okay? Now, notice that this green curve here, once I hit the gain bandwidth of the amplifier, right, it actually started having sort of a higher impedance, right? It actually had a 0 right at this point. Okay? Well, if I've got a 0 right at that point, right, and it basically starts flattening out, that implies that you would actually see a 0 in the overall impedance as well. But notice, actually, you can't really have this flat for too long, because there's no way you could ever have higher impedance than the capacitor itself. Okay? So if you zoomed in really, really carefully on this point here, what you'd see is that you'd have a 0, basically at the same point that you had a 0 here, but you'd also very shortly thereafterwards have a pole. Okay? Where that pole would be kicking in just to make sure that you keep following the capacitor curve. Okay? So far, is everybody with me, or? Okay, so by the way, I'll explain in more detail in 1 second why this is a very important thing. I will say that even with this, very small kink that I added here, this is actually somewhat probably exaggerated. But it's really important to know that this is there, because oftentimes this is like small enough that even in SPICE, you wouldn't even be able to see it unless you really simulated right around those points, looked very, very carefully. But if you aren't aware of the fact that it's there, it can actually cause pretty big problems in terms of your overall circuit behavior. Okay? And the reason for that is the following. This kind of response here, where you have a pole and a 0 very closely spaced from each other, is what's known as a pole-0 doublet. Okay? And so the thing that I'll sort of remind you all of is that if we were to look at just any generic, sort of second-order system, we were to ask ourselves, how does that thing respond in the time domain? So here I'm still going to be sticking with sort of our gain-boosted cascode example. So let's say as an example I asked you, what was the output voltage versus time if, for example, I was to feed in a current step? Right? And what I mean by that is, in this picture over here, I just take a current and I dump it onto that load right there. Okay, which, by the way, might indeed happen if I use this thing as part of a load inside of my amplifier, right? Inside of some operational transconductance amplifier. Okay? So this would be, for example, my I of t. Okay, well, if I have just some generic second-order system, then what you'll always get in terms of the output response is essentially something that looks like, at least as long as it's sort of overdamped, is something that looks like the composition of exponentials, or the time constants of each of the exponentials, is basically related to the poles in the system. Okay? So as an example, if I said that, just as an example, if I said that there was a pole, let's say here, let's call that omega p1, and let's say there was another pole here, let's call that omega p2. Then if I looked at the transient response, and I'm going to again exaggerate this fairly substantially just to make the point clear. If you were to look at this in time, you'd see something that sort of looked like this. Okay? Where the time constant of this would be 1 over omega p1. And the time constant of that, this is tau 1, this will be tau 2, is proportional to 1 over omega p2. Okay? So in other words, my output response is just the sum of two sort of exponential settling terms. One with the time constant. Oh, I'm sorry, I should have done this the other way. This is actually omega p2. And this will be omega p1 here. Okay, so in other words, whichever pole is at the lower frequency would have the larger time constant, right? So again, the reason this is very important is that even though you might not be able to see this pole on your graph over here, it shows up in terms of your settling response. Okay? In other words, there's always going to be some settling component that will have that time constant in it. And in particular, if you were to take this load and, for example, use it inside of some larger amplifier, and then in that larger amplifier, for example, you were to tie it into a bigger feedback loop, where you were trying to get a gain bandwidth that was, let's say, out over here somewhere, well, you'd be in trouble. Okay? Because this pole would show up. Actually, even after the feedback, it would still basically be in the same point, because it turns out the pole and the 0 would just meet with each other. Okay? And that pole would actually dominate your overall settling response. Okay? In other words, rather than you getting something, very quickly just respond to the step that you put in, there'd be this long tail, slow kind of thing that may not get you to the precision that you wanted it to be at. Okay? Now, turns out that how far apart the pole and the 0 are spaced from each other also sets sort of how big this residual settling you have to do from that long, slow pole would be. but it's fairly actually easy to work out exactly sort of what that relationship is. And again, that's something that you guys are going to do in your homework just to make sure that all of this stuff about, poles and zeros in the frequency domain, you can get a nice intuitive picture of it in the time domain. Yes?
Just to make sure, so when you said that the pole would show up as you dominate, you meant WP1.
Oh, well, okay, so this is something that's perhaps a little bit confusing. The situation I'm talking about here is, let's pretend that you took this whole structure, and just as an example, let's say that I use this as an amplifier. So instead of, and let me do it maybe in a different color to hopefully not cause confusion. So I'll do it in, I don't know, let's try this color here. So if, for example, I drove that with a quote-unquote input signal, and I actually took this output over here, and somehow I fed it back to there. Okay, so now I've got some real feedback thing. Well, notice if I'm doing that, this is kind of my dominant pole, right? So as I change the feedback, this is the pole that I'm going to be moving around. Okay? So what I'm basically saying is that if I built this whole thing and I tried to design the GM of that amplifier such that I could actually take this and move it out, for example, over here somewhere, meaning that's the gain bandwidth I was wanting, now this is going to be a big problem, right? Whereas if I was only looking around over here somewhere, that pole zero doublet would be outside of the frequency range I care about. Okay, so that's really the most important point, is that once you start getting into this gain boosting stuff, if you really want to make sure it works the way you intended it to, you better make sure that that pole zero doublet is outside of the frequency range you're interested in for your overall response. Okay, because if it's not, it's going to show up and it's going to cause some other thing that potentially could dominate your overall errors. In other words, you'd spend some amount of GM in this first stage here, and you wouldn't actually get the settling you were expecting, which is kind of a waste. Okay? Is this clear to everybody? Or? So by the way, this is again something you're going to be sort of working on in your homework to make sure it's absolutely clear. But the real take-home message is you have to be very careful anytime you have this sort of internal feedback loop like this, because it's almost guaranteed to generate these pole zero doublets. And again, you better make sure that that pole zero doublet is outside of the bandwidth that you're interested in. Now, obviously, the bandwidth you're interested in depends upon how exactly you're using the rest of the circuit, right? Because, for example, if I tied this into unity gain feedback, that would have a very different constraint than, for example, if I just tied it in feedback with, a gain of a half or a tenth or whatever the number would be. Okay? Does this make sense to everybody? Or? Okay, so if that's clear, then hopefully the sort of next thing, which is kind of a cute trick, will be clear as well. So if you guys remember, I said that in modern technologies, oftentimes you only get like a gain of 10 from your transistors, right? So that would say that, okay, if I went and I did like a cascoded amplifier, I'd maybe get a gain of 100. If I then do this gain boost thing, I'm now maybe going to get like, I don't know, a gain of maybe 1,000 or so, maybe 10,000 if I'm really good. But sometimes I actually need gain of like 100,000 or 1,000,000 or 10 million or even perhaps a lot larger than that if I want really, really super precise kind of circuitry. Well, so it turns out there's a guy named Yoon Chu who graduated actually here from Berkeley about, I think almost 10 years ago, maybe 8 years ago, something like that, who actually said, well, look, if I'm in a modern technology and I really need these super high gains, I can't really afford to do cascoding. I can do the gain boost, so you know what? Why don't I take a gain-boosted amplifier? So that would, for example, be this topology here. And then inside of that gain-boosted amplifier, gain boost it. Okay? So you can imagine you can keep applying this recursively, right? If you don't have enough gain from that, you can take the next amplifier inside of here and gain boost that as well, right? And so on and so forth up to, whatever ridiculous gain you happen to feel like getting. So this indeed works. It's a very clever trick. But there's hopefully one fairly obvious and perhaps major annoyance with this. So what's the major annoyance given the long discussion we just had? Yeah, exactly. You're going to add a ton of pole zero doublets into this thing, right? You better make sure all of them are way the heck out compared to anything you care about, because if they're not, you're going to have a whole mess of a nightmare figuring out what the heck your amplifier is really doing. Okay? So indeed, very clever trick. They did this to actually get some very, very impressive sort of performance numbers. Probably not the sort of first thing you'll do, but good thing to know about, because indeed there may be situations where you just need really, really high open loop gain, and there's kind of no other way to do it. Yes?
There
It will look somewhat similar to sort of the picture that I'm drawing here, but it's just that rather than just having one pole zero doublet, you'll have multiple pole zero doublets.
Oh, you meant for these amps, do you know what kind of frequencies they were getting?
I believe this was done for a few hundred megasample per second A to D converter. So I believe it was about 400 to 500 megasamples per second, which actually, as we'll talk about in a couple more lectures, doesn't necessarily mean that the bandwidth is 400 or 500 megahertz. It actually tends to mean that it's quite a bit higher than that, because when you're building those ADCs, you tend to want to make sure that these things settle to within very, very precise values. Okay, and again, we'll talk a lot more about exactly how you make that relationship in a couple more lectures. Okay? Is it 12? Oh, okay. No, you're right. So it's 11-bit, 12 megasamples. Yeah, okay. So, I got it off by an order of magnitude or something like that. But it's actually, I think there was another one that he did later that was even higher, higher speed than that. If you're interested, I can dig up the reference for you. Yes?
So for this nested gain boost, are you actually just adding pole zero doublets, or are you actually moving it to lower frequency?
Moving the pole zero doublets to lower frequency, you mean? So obviously it depends upon how exactly you've done the design in the first place. But really, I guess if you do it right, what you should be doing is adding more pole zero doublets outside of the bandwidths that you care about. Because again, if they're inside of the sort of gain bandwidths you care about or the bandwidths you care about, it'll cause problems. Now, it is true that sort of the poles and zeros of this will interact with the poles and zeros of the original circuit. So it is indeed going to be harder to ensure that that's the case. But if you have sort of, if you have enough bandwidth out of the technology relative to the sort of speeds you're trying to go at, it is indeed possible to push those out into frequency ranges that you would basically beyond where the signal really lies or where your real bandwidth that you're interested in is.
Because your gain bandwidth is still fixed, right? So if you're increasing gain.
Yeah, no, so that's right. But so remember, the gain bandwidth was all you're doing by playing this trick is increasing the output impedance, right? So in other words, what I'm really doing by playing that trick is taking that orange curve there and pushing it up. Right? So I'm making it look more and more like the ideal integrator. But I'm not changing the gain bandwidth, right? All I'm doing is trying to make the DC gain higher and higher. And it turns out that indeed, oftentimes you need that DC gain just to make sure that you settle accurately enough. Okay? Like, for example, if you want a 1 microvolt residual error off of, let's say, 1 volt signal, that translates into something like a gain of 1,000,000. Okay? That's the only reason you play this trick. Good. Other questions on this? Or? Okay, great. If not, let's go ahead and just discuss one last quick thing with respect to these current sources, which is so far, I said we can play these cascode tricks. It's really nice. It works very well. It gives you higher output impedance. But the next question you may ask yourself is, well, okay, do I have to pay anything for it, other than, of course, the Vmin? But in particular, do I have to pay anything for it from a noise standpoint? Okay? So it turns out there's actually some very interesting phenomenon that happen here, specifically in terms of the noise performance of these types of structures. So let me actually start this out by maybe taking a quick poll. Okay? And so let me number sort of each of these things one at a time. So let's call number 1, this is just your standard, regular current source. 2 is your cascoded current source. And 3 is a gain-boosted cascoded current source. Okay? It looks a little bit funny, but if you just sort of deconvolve this a little bit, this thing here is really just an amplifier, right? It's a common source amplifier. Notice it's looking at the source voltage. Its output is driving the gate of that cascode. It's really just a gain-boosted cascode. Okay? So let's maybe take a kind of quick poll. So if I compare the noise coming from current source number 2 versus current source number 1, who thinks current source number 2 has less noise? Same noise? More noise? Okay, so that is technically correct. But now let me ask you, a little bit more nitpicky. How much more noise is it? Is it like a lot? Or is it, yeah, there's a little bit more? A little bit. Okay, so for the guys who said a little bit, why is it just a little bit more? Okay, great. Okay, great. So you said actually exactly the right point. So just to make sure that everybody else gets it, I want to draw one very simple picture, right? So let's again remind ourselves that we call everything, or that we call what we study, circuits for a reason. And so let's draw the complete circuit. Okay? So if I look at, for example, the noise current from my original common source or uncascoded structure, then in order for it to create a noise voltage at the output that we measure, that current has to flow through that loop like this, right? In other words, it has to actually flow through that output resistance. Okay? Well, if I look at the noise current from the same transistor in the cascoded structure, indeed, most of that noise current should actually flow through the loop that includes that resistance. Right? Because if you think about it, the cascode, as long as it's sort of, been biased well and you have a reasonable GMRO and all that, largely speaking, you would just see the GM of that cascode device looking up, right? And so indeed, all of your current would basically just flow through that loop. Okay? Now, however, let's think about the cascode itself. And let me do this again in a slightly different color. So now let's add in the noise current of the cascode. Okay? And in particular, it's very useful to look at the current as if it's going to be flowing sort of in that direction that I just pointed to there. Okay? So in terms of the noise current from the cascode, when it looks down into that node right there, what are sort of the impedances that it sees? Yeah, so it's going to see the RO of the device below it, right? But it's also going to see the 1 over GM of its own, of basically that transistor, right? So as long as your 1 over GM is small compared to the RO of the transistor below it, that cascode current is going to be totally happy to just flow in a loop like that, right? In other words, it's going to recirculate inside of the transistor itself. Now, that's really good news from a noise standpoint, because notice, as long as the current is flowing through this internal loop, it has no effect whatsoever on the output voltage, right? Because, yeah, you change this Vs relative to ground, but if I'm measuring this output voltage relative to ground, who cares? Didn't do anything. Okay? So in other words, as long as you get this noise current to circulate internally here, indeed, that cascode should not be adding very much noise at all. Okay? Now, turns out that's obviously not 100% true, because indeed, there's always an RO here, so some percentage of the cascode current will flow through there. And in particular, there's always going to be some parasitic capacitance at that node. So that means that at higher frequencies, more of the cascode current will tend to flow through that capacitance, and therefore through the output and cause some additional noise. But so as long as you keep that capacitance small, which by the way you really do want to do for many, many reasons, including some of these settling things we talked about before, then indeed this cascode structure will not add a whole lot of noise to your output. So now, just to make sure that that's clear, or that people sort of understood that, now let's do another comparison. So who thinks that current source number 3 will have less noise than number 2? Okay, well, that's good. Hopefully that's the obvious one. Who thinks it'll have the same or about the same as number 2? Again, we're comparing 3 and 2. So 3 is the gain boost, and 2 is the cascode. Okay, so 1 brave soul, 2 brave souls said it's the same or about the same. Who says it's 3 brave souls? Who says it's more? Okay, so for those of you guys who said it's more, why do you say it's more? Other than just you guessed? Ah, okay. So this was the answer I was hoping someone would give, but now I'm going to challenge you. Okay? Because you're absolutely correct. There's going to be noise on that Vs there, right? And indeed, that noise is going to be amplified by that amplifier there. What's the equivalent model for that noise? Yeah. Oh, no. Okay, well, if that's what you're going to say, then. So if I take that AVVS, right, all that says is that I amplified the noise current of the cascode itself, right? But now let me, really push on it. Let's say that indeed my 1 over GM of that device is small compared to all of the impedance in the rest of the circuit. Does it matter that that noise current increased, or is it just going to recirculate through the same loop it was circulating through before? What do you guys think? This is one of those times where my tone should make the answer obvious. It's just going to recirculate, right? Because, hey, like we said before, putting that amplifier in just increased the effective GM of the device. So yeah, sure, the noise current went up, but so did the GM, right? So just like before, I'm just going to circulate completely within that transistor itself, okay? Now, again, everything I'm saying is only true to within, some, let's say, number of digits of precision, because indeed there's always ROs, there's always capacitance on the node, and so on and so forth. But nonetheless, indeed, the whole point is that by doing this gain boost, if you really do things right, you actually should not be modifying the noise very much at all. And in fact, if you think really carefully about what we said we had to do before, in terms of basically notice that, this amplifier had to be the dominant pole in that feedback loop, which means that this capacitance is going to kick in at a relatively low frequency. Well, that even means that we're actually going to be starting to filter out any of this amplification that would have been happening. Or perhaps more appropriately, we'd be filtering out any of the noise current from that amplifier that we added there in the first place. Okay? So it is indeed true that this will have probably slightly more noise than number 2, but actually all 3 of these should be very, very comparable from a noise performance standpoint. In particular, as long as you make sure that that capacitance on that source node, or this Vx that we typically call it, is sufficiently small. Okay? Because that's really the only dominant effect that causes you to really get a lot of extra noise current flowing through the output. So just to be sure that, oh, yes?
What about the noise
From this guy? Yeah, so that's what I was mentioning before, is that largely speaking gets filtered because of the fact that we had to put a cap there to make sure that that becomes the dominant pole of that whole feedback loop. Right? Because again, if it wasn't the dominant pole, then we would have had stability problems and it would be really hard to make this whole thing work in the first place. So just to repeat for the online audience, the question was, what about the noise of that device? And I was just reiterating that I typically have to put a capacitor there anyways just to make that the dominant pole, and therefore that noise also tends to not be a dominant overall effect. Okay? So this picture here is just sort of showing a simulation, basically repeating everything that I just said. So it's showing you, and I apologize for the labels not being so great, basically this sort of green line that you probably can't even see, so let's not even compare it. The pink line versus the blue. Pink there is number 2, in other words, just the cascode. Blue is the gain-boosted cascode. And what this plot is showing you here is basically the noise density versus frequency. In other words, the power spectral density of the noise. You can see there's a 1 over f component down here. There's some white stuff. And then what you see is that, indeed, you maybe pick up a little bit of extra noise from that boosting circuit there. But overall, it's very, very comparable to the original cascoded current source. Okay? And again, you in fact can't even really see the just sort of green line, because basically it turns out to be almost right on top of that pink line there. This bottom panel here is just showing you what the sort of total integrated noise is across all frequencies, or rather across, let's say, from 0 to whatever frequency is listed on the x-axis. It's just showing you that indeed there is some small penalty in the noise, but typically not too substantial, especially if you've done this the right way. Yes? This little hump here? Ah, okay. So actually, this turns out to be directly related to my choice for the phase margin of that boosting loop. Because basically, it just means there's a little bit of peaking in that boosting loop. And so you're seeing that show up in the noise behavior as well. But you can see it's a very sort of small effect, right? Okay, so just one final sort of quick thing before we close out with current sources and move on to something slightly more, at least complicated, I should say, but also hopefully more interesting. We spent a lot of time sort of talking about noise performance and things like that, but it is sort of useful to just give ourselves a rough rule of thumb as to how you will typically size these cascoded current sources. Okay? So let's ignore all the biasing and stuff for now. Let's assume we can magically generate that. So turns out you're typically going to want to do things slightly differently from that bottom device versus for that top cascode device. So in general, if you just wanted sort of a good current source, how you tend to size those? What's the sort of common choice that you'll make? And by the way, when I say size, I really mean channel length and V star. So what's the typical sort of choices you'll make? And I don't mean a number, obviously. I just mean relatively speaking. What's the number one, most important thing about a current source?
High output impedance.
Yeah, high output impedance, right? So, okay, at least at DC, for the transistor, what are you going to do to make it have high output impedance? Let's start with channel length. Yeah, make it long, right? That's indeed the most common thing you'll do is you'll pick a long channel length, okay? How about the V star of that device? What did we say we wanted there, particularly from a noise standpoint? Well, okay, so you said we wanted the bottom to be higher than the top. That is going to turn out to be correct, although here it's really the current source relative to the GM that matters. But nonetheless, indeed, we want a relatively large V star, at least to the extent that it doesn't eat into our swing, because making that V star large will help us from a noise performance standpoint. Now, again, you have to be a little bit careful with this, and that's really why I put this in quotes, because obviously, again, there is that trade-off between the minimum voltage across the current source and the noise you get. But it basically says you're going to make this kind of as large as you can while still meeting the swing that you want to get. Okay? Now, how about that current source device? What are we going to want to choose for the channel length of that? What do you guys think? Yeah, you're probably going to want to choose a small channel length here. Now, why is that? Okay, you're going to get higher GM. That's correct. What else is actually pretty important? And I'll just give you a reminder. We said that we want high output impedance. And notice I did not say resistance. Yeah, parasitic capacitance, right? Because notice if I make that short channel, that will reduce the parasitic capacitance that's sitting there, right? So this is actually a very common and nice trick to make it so that you can not only just get high output impedance at DC, but you can also actually reduce the AC output impedance at least up to a certain frequency. Okay? Because by making this sort of a short channel length device, indeed I can reduce its drain capacitance, which, again, if I've done things right, is the dominant sort of loading on the final output. Okay? So indeed, you will tend to make that a short channel length. But how about V star? What are you typically going to choose there? Yeah, you're probably going to choose a reasonably small V star. Why is that? Yeah, exactly. Your noise is going to circulate anyways, right? And you probably want a reasonably high GM for the same bias current. Okay, now, there's obviously a little bit of a trade-off here, because if you make the V star too small, you'll have a lot of parasitic capacitance. In other words, the FT of that device will get too low. But again, that's why I sort of put things in quote here. It is indeed the case that if you sort of looked at a typical design, you will tend to choose a smaller V star for that cascode device, but also a shorter channel length to really minimize its capacitive parasitics. Whereas for the current source itself, you'll tend to use a longer channel length. And if you can, also even a larger V star as well, just to really reduce the noise that it generates in the first place. Okay? So again, this very sort of common sizing methodology that people will use just to try and sort of get a little bit of the best of both worlds, right? Both to get a relatively low output capacitance and to get a very high DC impedance. Okay? Does this make sense to everybody? Or? Yes?
Don't you also hurt the output impedance at DC by having a smaller L because then you have less DC?
Fair enough. It is true that the GMRO of that cascode device wouldn't be as high as if you made it the longer channel length. And so sometimes you'll make that optimization. You may make it long channel as well. But I mention this because oftentimes this turns out to be sort of a nice composite structure, and that if I'm not limited just by the DC impedance, but I actually care about high impedance across all frequencies, then this is indeed a sort of nice compromise to be made. That's really what it comes down to. So again, none of these, everything here should be in quotes, because I'm not saying that in all circuits they always look like this. I'm just mentioning it because indeed this is a sort of fairly typical design point that people will find themselves in.
Yeah.
It's a good question.
Doesn't necessarily mean minimum, right?
You mean by V star here or channel length? Oh, yeah, it very much depends on the technology. Indeed, sometimes you'll bump that ever so slightly above minimum, simply because the RO will improve much faster than sort of the parasitics will. That's also a very common choice. Yes?
Just to check, so if you have a current source, like the noise current coming from the upper transistor,
From the Cascode device? Okay.
why doesn't that see the impedance? Like, why does that see the impedance at the sort of middle node and not the impedance at the top?
Oh, okay. So the question was, if I add in sort of the noise current source, and I'm just going to draw it on the side here so that I don't clobber other stuff. The question was, if I look at that noise current source, why is it that it's sort of only seeing the 1 over GM here down at this bottom node as opposed to the impedance looking down over there? It's not at all that it doesn't see one versus the other. It's simply a question of when I sort of solve this overall circuit, what's easier for me to calculate in the first place? What's easier for me to see what causes the current to divide one way or the other? Because basically, to figure out the path that goes up over here, what I need to know is what was the impedance looking down, and then I have to come back through the loop. Whereas in terms of basically, or rather, if I was to say, if I tried to look at the current divider right here, it'd be really hard because I maybe know this impedance, but I don't know the source voltage. Right? And this GM is only pointing one way and is only dependent upon Vs. Right? Whereas if I look down in this node, right, I know what Vs is because that's directly a function of the current I'm injecting in the first place. So it's just easier to calculate that current divider based upon looking at sort of KCL at that node. So to say it another way, physically speaking, nothing I've said is violating any basic laws. It's just that I looked at it that way, and it turns out to also give you the sort of right intuition at the end of the day as to where most of this noise current would be circulating. Okay, great. Unless there's other questions on this, let's go ahead and at least briefly start talking about the next set of lecture notes. So this is lecture notes number 9, which I handed out, I believe, last time. And as I mentioned before, now that we've sort of understood a bit about how we use current sources, either for biasing purposes or as sort of an active load for our amplifiers, let's talk a little bit about how we're actually going to build or, in fact, use the amplifiers themselves. Okay? So the first thing that I want to just point out is perhaps some terminology that you've heard before, but I want to make sure that it's absolutely clear to everybody as to what really the difference is. Okay? So you've probably heard many times about, obviously, op amps. That's probably actually the first thing that you learned about, back in your original, Intro to EE class. But turns out that in most of what we do in IC design, it's actually OTAs that'll be the sort of most fundamental building block. So to be clear, an OTA stands for Operational Transconductance Amplifier. And really the biggest difference between an OTA and an op amp is that in an op amp, you basically assume it's a controlled voltage source, meaning that its output impedance is 0. Okay? In an OTA, you actually assume it's a controlled current source. In other words, its output impedance is infinite, or as large as you can possibly make it. Okay? So in many ways, these two are very, very similar, right? You still want infinite input impedance. That's true for both. But again, the big difference is in an op amp, 0 output impedance, whereas in an OTA, you basically have an open circuit output impedance. In both cases, you still want basically quote-unquote high voltage gain. And I put this in quotes because obviously in an OTA, you don't really have voltage gain. You're actually moving from voltage into a current. But obviously in any real circuit, there's always an output impedance here, so you can indeed define a so-called voltage gain. Okay? Now, the reason I want to make this distinction, as you'll see in 1 second, is that depending upon whether you're using an OTA or an op amp, that's also actually going to change the way you're going to want to use these in larger closed-loop systems. Okay? The other point that I just want to briefly mention, which should hopefully be obvious, is if you went and you built kind of pretty much any straightforward transistor amplifier that I know of, what you're really typically going to get is not an op amp. You're actually going to get an OTA. Right? Because if you think about it, if I just took this simple common source amplifier here, right? I take an input, I go through a GM, and I dump it into hopefully a high output impedance to get to the output. In other words, indeed, this is really an OTA and not an op amp. Okay? In fact, as we'll see a little bit later on, if we actually want to build an op amp, you'll have to do something. You'll have to add extra stuff onto this in order to take your OTA and convert it into an op amp. Okay? Is this clear to everybody? Or? Okay, so why is this sort of an important point to realize? Well, having really, really high DC gain is, of course, great, but typically is not that easy to use just by sort of, taking that op amp and throwing inputs into it. Right? Typically, you put things into feedback to actually know what the gain you're applying is, right? And also to make sure you don't, just rail out all of your signals. Okay? So obviously, the classic way or the simplest way to do that is just add some resistors into this feedback network. And indeed, if you've got an op amp, your open loop voltage gain is indeed infinity. And because you have zero output impedance, doesn't care what the value of these feedback resistors are, right? No matter what those resistors are, you'll always get essentially the same open loop gain. Well, if instead I actually use an OTA, which again as a reminder is basically what you're going to get in most transistor amplifiers, well, now unfortunately those resistors are actually going to reduce the effective output impedance of the amplifier, right? In other words, your open loop voltage gain will actually depend upon the value of these resistors, right? In other words, the feedback is really loading your OTA. Now, that's bad news because, I don't want to spend any more GM than I have to, right? And remember, GM is only set essentially by the capacitance you want to drive in the first place. So that if I add in these resistors, I may have to sort of artificially up my GM now just because of the DC gain constraint and not because of the real capacitance that I have to drive in my system. Okay? So you could say, well, okay, maybe I'll just make these resistors artificially very large, which you can do, but takes a lot of area, has a lot of parasitic capacitance, therefore introduces parasitic poles into your overall system. Generally, bad news. Okay? So as we actually already hinted at before, we're going to look at a somewhat different solution to basically allow ourselves to build feedback amplifiers or feedback systems, but not actually suffer the effects of putting loading onto our OTA. Okay? So in particular, the way we're going to do that is with capacitive feedback. Okay? Now, the reason this is really nice is that, again, if it's a capacitor, at least at DC, it doesn't load our output whatsoever, right? In other words, it doesn't reduce the impedance any more than the impedance we would have naturally gotten from that amplifier in the first place. Okay? Now, of course, if I have a capacitor, that is going to cause loading onto the output at higher frequencies, because just like any other capacitor, the impedance is going to drop. But hey, that's going to happen in all amplifiers anyways, right? And in particular, as long as I can make this capacitance reasonably small in comparison to the load that I'm driving, it's not going to have a very big impact on my overall sort of capacitive loading. In fact, if you even remember, we said that we were basically going to have the series stack of these two capacitors, which was going to mean that I really get an even smaller cap than I would have thought just from any one of these two individually. Okay? So this sounds great, and indeed, actually, this is something we're going to be using quite a bit. But unfortunately, what I've drawn here, if you literally just took it and plugged it into SPICE, would not quite exactly work. Okay? So in particular, if you indeed took exactly the circuit that I drew here, and you tried to simulate it in SPICE, what would happen? What would SPICE do? Yeah, exactly. It would basically come back and say, sorry, convergence error, no DC path to ground from node VX, right? So what's the problem? Why? And by the way, SPICE is absolutely correct in this case. So what's the real practical issue? Why if you built this circuit in reality, would it actually not work just like SPICE is basically telling you? What's the problem? Yeah, exactly. So basically the problem is if there's no DC impedance there, you have absolutely no freaking clue what that voltage is at DC. Okay? So just as an example, let's say that I was working in a 1 volt power supply technology. Okay? And from whatever weird reason, I don't know, some particles from space happen to land on your chip, which by the way is totally possible. Or, I don't know, there's just, some small leakage from one wire to the other through some, hole in the oxide, or pretty much any one of a billion other things. And you've got 1 femtoamp of leakage there. Okay? Well, trust me, if there is no other path for current to flow, if you wait long enough, and somehow magically that femtoamp comes from some source that can go up to whatever voltage it wants to. Well, indeed, this could go, for example, to 10 volts, or minus 10 volts, or I don't know, 5 or 15 or whatever you want. Okay? Hopefully it should be pretty clear that if you were to put that into the DC input of your poor transistor amplifier with a 1 volt supply, it would die, right? It would do absolutely nothing useful. Okay? So the point is, indeed, you can't just go and sort of take these capacitors just by themselves, because, again, you have no idea what the input to that amplifier actually is at DC. And pretty much any amplifier that we work with, we assume that it has some reasonable value at DC in order to ensure it actually behaves the way we expected it to. Okay? So how do you guys think we can solve this? What's the solution? Switches. Okay, well, what are you going to do with the switches? Yeah, exactly. So the first thing you can do is you say, well, screw it. The problem was that I didn't know what that stupid Vx was at DC. So let me just put in a switch so that at least at the beginning of time, I can set that Vx to some known value, right? So this is like the simplest thing I could think of, right? I could just take some switch. In this case, I reset it to ground, okay? This doesn't really mean necessarily ground, by the way. This could be like incremental ground, but that's not too important exactly what the value there is. And I could just say, okay, well, fine. I'll just force it to some known value, at least initially. Okay? So I would claim that this is still not quite good enough. Okay? We could indeed just do this, or we could try and do this just once at startup. But even then, it's still kind of dicey, right? Because, okay, let's say indeed you did this once at the beginning of the chip, starting on, which let's say corresponds to your phone being on. Well, if you only did it once and then your phone is running for like a day, a week, even a few hours, you could still have this node just drift off at DC, or quote-unquote DC, to some weird new bias point, right? And if it drifts off to that weird new bias point, well, crap, thing stops working, right? And then you get upset because it drops your call or crashes Facebook or whatever the heck you happen to be doing at that time. Okay? So instead, you can't really just do this once. You're actually going to have to repeatedly reset that amplifier. Okay? Or in other words, repeatedly reset that Vx there. Now, as I'm indicating here on the slide, you're usually going to do that reset actually not just sort of once every, let's say, 100 cycles or 100 uses of that amplifier. You're actually probably going to do it every single time you use the output of that amplifier. Does anybody know why that is? Why is it that I claim you actually really want to do this basically every single cycle or every single time you use this amplifier? And by use, I mean basically because of the way this is going to work, we're now going to be moving into the sampled domain. So in other words, every time we take a sample at the output of that amplifier, we're probably going to want to have reset it first. So why do I say that that's important?
So you don't have any residual effects from a last sample?
Okay, you said so that I don't have any residual effects from the last sample. That is true, but let me be sort of a little bit more explicit to sort of make sure it's clear. By the way, this particular thing may or may not exactly get rid of the effects of the last sample. It will get rid of it on this Vx node. It may not get rid of it everywhere else, which we'll come back to in 1 second. But even just for this one node here, what would be bad about, for example, only doing this once every 10 samples as opposed to once every 1 sample? Why would that be not so great? What's the potential problem it would cause? Okay, you said that you could build up charge in the feedback capacitor. That is true. I think that's actually very similar to what Jethro was saying, which is there may be some history in terms of sort of the samples that you're getting intermingling between each other. But maybe I'll sort of give you another hint or another sort of idea as to what could happen. I drew this thing as kind of an ideal switch here. But most switches, when you either turn them on or turn them off, push some charge in and out of the output. Okay? So very commonly, and by the way, we'll talk a lot more about this later on down the road, if you were to build that, for example, out of an MOS transistor, then every time you were to turn that transistor on and off, if you looked at sort of the current flowing through it, even independent of any change in voltage it was making, you'd basically see these glitches in current from charge basically coming into the channel or being forced out of it. Okay? So that would actually mean that every single time you turn that switch on or off, there's probably going to be some residual error on that Vx node. Okay? So actually, that's really the main reason you tend to do this every single cycle. Because simply by the process of turning that switch on or off, if you're going to create an error, you now have a choice. Either I'm going to create that error, for example, once every 10 cycles, in which case, when I look at my output, every 10 cycles will be corrupted by that error, and all of the other 9 cycles will not, which means I'll see this signal that's repeating at 1 every 10 cycles, or this error signal, I should say. Or if I do this every single cycle, then now what's going to happen? If I repeatedly turn this switch on every single time I sample the output, or turn it on and off every time I sample the output, what's going to happen in terms of that error? What's it going to look like at the output? Systematic by, what do you mean by that? Yeah, it's the same every time. So in other words, it looks like just a DC offset, right? Because every time I use it, it's always the same error. And so if I can just estimate what that DC effect is, or really what that repeated effect on every single sample is, I can basically just knock it out, right? So in other words, it just turns out that oftentimes if you have to create an error, you'd prefer to just make that error sit down at DC so that it's really easy to figure out what the error is and just knock it off in the first place, okay? Whereas if, for example, you just did this once every 10 cycles or so, now you'd have this repeated, once every 10 cycle, basically spur sitting in your output spectrum, okay, which is typically bad news. Does this make sense to everybody? Or? Okay, so we'll pick back up with this not next week, but the following week. So again, just be on the lookout for the homework. We'll be posting that within the next